In this video, we're going to talk about computing the discrete Fourier transform as a matrix vector multiplication. To begin, I'd like to just review the idea of matrix vector multiplication. So let's begin with saying that the vector y is the product of some matrix A times a vector x. In this video, when I'm referring to vectors, I'll use this underscore to denote vectors and capital letters to denote matrices. In this case, this matrix A will be n by n. So this means that the vectors y and x will have this form as shown here. So y will have elements y0 up to yn minus 1. That's an n by 1 vector. Similarly, x will have elements x0 up to xn minus 1. I'm using subscripts to denote the elements of the vectors. And then the matrix A will have this form. Its first element will be denoted A with a pair of subscripts, the first subscript to denote the row, and the second subscript to denote the column index. So this would be A0 n minus 1. And then as we go down to the bottom row, this will be A n minus 1 comma 0. Over to the last element in the matrix is A sub n minus 1 comma n minus 1. So as described above, this is an n by n matrix. When we multiply a matrix times a vector, let's just draw a picture of what that would look like. So here's a picture of the vector y, and that's equal to a square matrix A times a vector x. So this is y is equal to the matrix A times the vector x. And if we want to calculate, say, the kth element of the result, so I'll say this is the kth element here, that's going to be, you know this from your days in linear algebra, that's going to be the kth row of the matrix A times the elements in this vector. So we do we multiply the elements, the first element in each vector times plus the product of the second elements in these two vectors, and so on and so on and so on as we work our way across. Let's denote the let's pick an arbitrary column. Let's say it's the nth column of the matrix, and let's denote the element in that nth column on the kth row. So this would be A sub k comma n, because again it's on the kth row and in the nth column. And that element will multiply the nth element in the x vector. So if we want to write out an expression for the kth element of the output vector, we could write it as the sum, n going from 0 up to n minus 1, of a k comma n times x sub n. So this is up here, this notation describes how we write things out in matrices and vectors, but in terms of the components, this shows how we would describe the matrix vector product at the component level. The reason that we can describe the DFT as a matrix vector multiplication can be easily seen now if we write down an expression for the DFT next to the component-wise matrix vector product. And if we compare these two, we see a relationship. So here we have the output at position k, for the matrix vector product, and here we have the output of the DFT in frequency bin k, and it's equal to a sum over n elements. Up here in the matrix vector product, we see that the first quantity here inside the sum is a function of two indexes, k and n, and we see that same structure appear here, where this complex exponential is a function of both k and n. In this case, the functional form is a product, but that doesn't matter. The point is that it's a function of two indexes, k and n. And then finally, you can see that up here we have x sub n, and down here in the DFT we have x at position n, time index n. So if we define a vector, or a matrix rather, let's call it W, and we say that its k-nth element is equal to e to the minus j 2 pi k n over n. So this is the notation that I'm using to describe the k-nth element of the matrix W. If we define it to be this complex exponential, then if we stack the time domain samples x n and the frequency domain samples capital X k into vectors, then we can write the DFT in matrix vector form. So I'll write capital X vector, so this contains all n of the values of the DFT. That would be equal to this matrix W times the vector little x. Again, that contains the samples of the time domain sequence that we're transforming. So by doing this calculation, we can calculate the DFT using a matrix vector product. The key here is simply to go back to the DFT expression and just recognize that this has the same form as a matrix vector product. So nothing really too fancy going on there. While we're in matrices and vectors, though, it might be worth also looking at what the inverse transform would look like. So if the forward transform has this expression, we could multiply both sides of this expression by the inverse of W and calculate the inverse transform. So let's see, this would be W inverse times capital X. This would be the inverse DFT. And what I'd like to do is take just a minute to explore the structure of this W inverse. Let's explore the structure of the inverse matrix by writing down the inverse DFT in its component form. Actually, when we're doing the inverse transform, we have a plus j in the exponent. And so again, just using the same idea as before, we recognize in this summation the presence of a matrix vector product. The elements of the matrix are given by this scalar out front times this complex exponential. And so so what this tells us is that we know that the components, or the elements of W inverse, let's say this is the n-kth element, are given by these complex exponentials. So let's just write this out here as 1 over n e to the plus j 2 pi kn divided by n. That must be the n-kth element of this matrix. But pushing this a little bit further, we can write this as 1 over n times e to the minus j 2 pi kn, and then we'll conjugate that. So we've conjugated twice, once on the inside by putting a minus j, and once on the outside using the conjugate operator. Let's push this along a little bit further even, because now what we do is we recognize this as the knth element of the original matrix that we had, but it's conjugated now. So we see that the nkth element of W inverse is equal to the knth element of W conjugate. And to get an exact equality here, we can interchange these two subscripts if we transpose the matrix, because transposing the matrix interchanges rows and columns. So let's apply that. Transpose. So inside we'll have W conjugate transpose, and now we can call it n comma k. So this actually gives us an expression now for W inverse. W inverse is equal to 1 over n times W, and I'm going to write an H here. This H stands for Hermitian transpose, where the H is equal to a conjugation and of all the elements of the matrix, and then a transpose of the matrix. So this is interesting, because normally inverting a matrix is very hard, but we see that all of this needed to invert this special matrix W is to transpose and conjugate all the elements and then divide by n. So what we've just found then is that let me write it like this. We know that the identity is given by W inverse times W, or that 1 over n times W conjugate transpose times W is equal to the identity. And by the way, a matrix that has this type of structure is called by various names. Unitary is one of the names that it is appropriate here. Actually, it's almost appropriate, because a unitary matrix, we would split this 1 over n scale factor among both of these by multiplying each of them by 1 over square root n. But anyway, a matrix that for which its inverse is its transpose is called an orthogonal matrix. And I would like to explore this relationship just a little bit more, because I think there's one more piece of information that we can glean by exploring that in greater depth. So let's take a look at this product W conjugate transpose times W. And what I'd like to do to explore this product is to look at a particular element of this matrix, and let's examine the L-mth element of this matrix. So if we were to just diagram this out, here's W conjugate transpose. I'll put that here, W conjugate transpose, and then here's W. And if we're looking at the L-mth element, what we're doing is we're taking this row, the Lth row, times the mth column of W, and we're going to look at that product. So what we have here is a summation going from n equals 0 up to n minus 1 of e to the j 2 pi ln over n. Those are all of the elements on this Lth row of the matrix. The reason we don't have a negative sign here is because H is a conjugate transpose. So the conjugate removes the negative sign. But remember, W has a negative j on it, e to the minus j 2 pi mn over n, and we're summing on n as we move across this row and down this column. Well, we can put those two exponentials together, So we have e to the j 2 pi L minus m times n divided by n. This is a straightforward geometric series, and there are two cases to consider. The first case is where L is equal to m, and in that case it's fairly straightforward to see that when L is equal to m, this quantity is 0, the whole exponent is 0, so e to the j 0 is 1, and then we're summing 1 n times, and so we have that this is equal to n when L is equal to m. And when L is not equal to m, we can use the geometric series formula, so this would give us 1 minus e to the j 2 pi L minus m times the upper limit plus 1, so that would be n, divided by n. And in the denominator we have 1 minus e to the j 2 pi L minus m over n. And what we notice if we do a little bit of algebra here on the exponent is that the n's cancel, leaving us with e to the j 2 pi times an integer. So remember that that is going to give us a value of 1. So in the numerator we end up with 1 minus 1, and so we get 0 in the numerator. The denominator is not 0 because L is not equal to m, and so we just get 0 out of this for the case L not equal to m. In other words, what we have is this is n times delta L minus m, where that is a Kronecker delta. And this probably should not surprise us, because if we go back to an expression we derived earlier, we see that if we rearrange this expression, another way to write this is that W conjugate transpose times W is equal to n times an identity matrix. And this delta function is telling us the same thing. Remember that the structure of an identity matrix is this would be n's along the diagonal, because it's n times the identity matrix, and zeros off the diagonal. Well, this expression that we've just derived tells us the same exact thing, in fact, because what we've seen is that if I take the inner product, or if I multiply these two vectors together, the Lth vector and the mth vector, I get 0 unless L is equal to m, and then I get n out. What this tells us really is that the columns of the DFT matrix W are orthogonal, or they're, in a geometric sense, they're 90 degrees apart. Okay, I want to introduce you to a few things in Matlab related to these concepts that we've just talked about. And in particular, Matlab has, let me shift gears here for a minute. Matlab has a function called DFT Matrix, DFT MTX. And if you pass in the value of n, which is the number of points in the transform, it will return this matrix W that we've been talking about. I want to just illustrate a few of these for you. First of all, let's look at W2 for a 2-point transform. Notice that this, if we were to multiply a vector by this matrix, a 2 by 1 vector, it would return the sum and the difference of the elements in the vector. We can just illustrate this as W times 2 comma minus 1, let's say. So that's going to return the sum, which is 2 plus negative 1, that's 1, and the difference, 2 minus negative 1, that's 3. So the Fourier transform or the DFT of the vector of the sequence 2, -1 is the sequence 1, 3. Things get a little more interesting if we go to higher order transforms. Here we are with a 4-point transform, and this one's sort of difficult to see what's going on. So if we take the real part of this, you can see then that what the action is when we multiply by this 4-point transform matrix. What it does is to calculate the DC bin of the transform, we just add together all of the elements of the input vector. And then to calculate the next output, we're going to multiply by this sequence. We should also take a look at the imaginary part of W. So the full W matrix has this structure where we have 1s on the top row, which is all real, and then it alternates between +1, -j, -1, +j, and so on as we move across the rows of the matrix. So we can get greater insight here, let's do another one. Let's make a 64-point transform. And instead of looking at the elements individually, let's maybe construct an image out of this. So you can see over here on the right that we have these two matrices, the real part of W and the imaginary part of W. It's an interesting looking pattern, but what does it really mean? Well, it's hard to see it here, so maybe what we should do is make a plot. But if you look across any row, you can see that the top row is a constant, and then the second row is 1 period of a cosine, the third row is 2 periods of a cosine, and so on. Let's illustrate that by saying plot real W. And in fact, I'm going to transpose because of the way the plot function works. And now if we come over here to the plot window, it's a big jumbled mess. So to try and peel this apart, what I'd like to do is select some of these and change the line width so that we can focus some attention on them. So this is actually the second row. The first row is up here at the top, and let's see if I can select that. The first row is up at the top, and that is a constant. Then the second row is this single period of a cosine function. The third row is going to be 2 periods of a cosine function. The next row if you can see that, that's 1, 2, 3 periods of a cosine, and let's do one more. I don't know if I can select it anymore. So this is actually, if you are able to see this, this is 1, 2, 3, 4 periods of a cosine function. So what is the DFT matrix W? It contains all integer numbers of periods of cosine in the real part and integer number of periods of sine in the imaginary part. That's what this DFT matrix contains. And just to illustrate a point here, let's generate a random vector, or let's use a vector of all ones. 1's 64 by 1. And I'll use a capital X for the FFT of X, and I'll use X DFT to be W times X. Now, X DFT and X should be equal. So to test equality, let's do the following. Let's just say X minus X DFT. And it looks like they're not equal, but in fact they are, because these numbers are all very, very small. All of these numbers are times 10 to the minus 14. So to numerical precision, we get the same answer whether we calculate the FFT using the FFT function or using a DFT using a matrix vector product.